In Episode 8, titled 1.1, Understand Tables and Schemas, Facts, Dimensions, Slowly Changing Dimensions, the focus is how schemas support consistent reporting and why consistency is the foundation of trust in data work. The CompTIA Data Plus DA0-002 exam often tests whether a candidate can reason about how tables fit together, not just what a single table contains. When reporting changes unexpectedly from one run to the next, the cause is frequently not the charting tool but the structure beneath it, including keys, joins, and assumptions about what a row represents. A clear schema reduces ambiguity because it establishes what fields mean, how tables relate, and what kinds of questions the data can answer reliably. The goal in this episode is to make the terms facts, dimensions, and slowly changing dimensions feel practical so they become decision tools rather than vocabulary. A schema can be defined as the set of rules that describe how tables and fields are organized, including names, data types, constraints, and relationships. It is the blueprint that explains what columns exist, what values are allowed, and how one table can reference another through keys. A schema also implies how data should be interpreted, because a field named order date should have a consistent meaning and a consistent format, and that consistency is what makes comparisons valid. In many environments, the schema is enforced by the database, but the deeper point is that it is enforced by the organization's shared understanding of the data model. When a stem on the exam mentions schema changes, mismatched fields, or inconsistent reporting, it is often pointing towards schema issues rather than purely analytical mistakes. A candidate who understands schema as both structure and meaning is better prepared to choose defensible answers. Facts are best explained as measurable events, where each row represents something that happened and each numeric field represents a measure that can be summed, counted, or averaged. Examples include a sale, a click, a page view, a shipment, or a support interaction, where the event is concrete and tied to time and context. The measures might be revenue, quantity, duration, count, or cost, and the key idea is that facts are where the math lives. Facts tend to grow quickly because events accumulate, which is why fact tables can become large and why performance and grain decisions matter. On the exam, language like transactions, events, metrics, or measures often signals that a fact table concept is in play. Recognizing that signal helps with questions about aggregation, double counting, and join behavior. Dimensions are best explained as descriptive context that explains who, what, where, and when for the facts. A dimension table often contains attributes like time periods, regions, products, customers, channels, or devices, which allow facts to be grouped and filtered in meaningful ways. The key idea is that dimensions provide labels and categories that make reporting understandable, because a raw metric without context rarely supports a decision. Dimensions tend to change more slowly than facts, but they do change, which is why the concept of history matters. In a reporting setting, a dimension might answer questions like which region, which product category, or which customer segment, while the fact table answers how many and how much. On the exam, terms like lookup, attributes, descriptive fields, or categories often indicate a dimension concept. A simple retail story is a reliable way to visualize a star layout because retail naturally includes events and descriptive context. The fact table might represent line items for purchases, where each row captures an item sold, the quantity, the price, and the sale time. Surrounding that fact table, dimension tables might include a product dimension with product names and categories, a store dimension with location and region, a customer dimension with segment and sign update, and a time dimension that breaks dates into year, quarter, month, and day. This star shape works because the fact table sits in the middle, connected to each dimension through keys, and most reporting questions are answered by joining the fact to a few relevant dimensions. The star approach keeps reporting consistent because measures come from the fact and labels come from dimensions, which creates a repeatable mental model for aggregation. Exam stems that mention star schema, dimensional modeling, or reporting performance often want the candidate to reason in this structure. Keys matter because they keep relationships stable over time, and stable relationships are what prevent subtle reporting errors. A key is a value used to connect tables, and in dimensional models, there is often a distinction between a natural key and a surrogate key. A natural key is a real-world identifier such as a product code, while a surrogate key is a generated identifier used to represent a row in a dimension table. Surrogate keys are often used to manage changes over time, because the real-world identifier might remain the same while descriptive attributes change, and the model may need to preserve history. When keys are chosen poorly, joins become unreliable, and analysts can end up with missing matches, duplicate matches, or shifting relationships that change totals unexpectedly. Exam questions often test whether a candidate notices that keys are the foundation of correct joins and therefore correct reporting. Snowflaking introduces trade-offs because it normalizes dimension tables into additional tables, which can reduce redundancy but increases complexity. In a star layout, a dimension might contain many attributes in one table, making joins simple and queries straightforward. In a snowflake layout, some of those attributes might be moved into separate related tables, such as splitting a product dimension into product, brand, and category tables. This can improve reuse and reduce repeated text, but it also adds more joins, which can affect performance and make queries harder to reason about. The exam angle is often about recognizing that snowflaking can be appropriate when reuse and consistency across multiple models matter, but it can also introduce confusion and increase the risk of incorrect joins. A seasoned analyst chooses snowflaking intentionally rather than by default, based on how the data will be used and who will maintain it. When stems mention complexity, reuse, or performance, they often point toward this trade-off. Slowly changing dimensions describe a real problem. Descriptive attributes change, but reporting still needs to be correct and explainable. A customer can move to a new region, a product can be rebranded, or an employee can shift departments, and those changes affect how historical facts should be interpreted. A slowly changing dimension is a dimension where attribute values change over time, and the model needs a rule for whether history is preserved or overwritten. The need for this concept appears whenever reporting must answer questions like what was true at the time of the event versus what is true today. The exam often tests whether a candidate recognizes that dimension data changes is not a small cleanup issue, but a modeling decision that affects trend accuracy and auditability. Understanding this concept turns confusing reporting discrepancies into a predictable outcome of chosen history rules. Type approaches compare how history is handled, and the common distinction is whether the model overwrites, preserves, or adds new rows when attributes change. One approach overwrites the old attribute values, which keeps the dimension simple but loses historical context. Another approach adds a new row for the new version of the dimension entity, which preserves history but requires keys and effective dates that can connect facts to the correct version. Another approach adds columns to store previous values, which preserves limited history but can become awkward as changes accumulate. The deeper point is that each approach is a policy choice. and the right choice depends on reporting requirements, governance expectations, and the meaning of trends. Exam stems often hint at whether history must be kept, such as compliance reporting or long-term performance tracking, and those hints guide the correct selection. The candidate is usually being tested on reasoning about consequences rather than memorizing type labels. Double counting is one of the most common reporting failures, and it often comes from not checking grain and join behavior. Grain means what one row represents, such as one sale, one line item, one customer per day, or one session, and the grain must be clear before measures can be summed safely. When a fact table at a fine grain is joined to a dimension table that introduces multiple matches, totals can multiply without any obvious error message. This is why stable keys and clean one-to-many relationships matter, because a fact should match one dimension row for each dimension, not several. Exam questions often describe totals that suddenly increase after a join, and the intended reasoning is to suspect grain mismatch or join duplication. The professional habit is to confirm grain explicitly and to treat joins as transformations that can change counts, not as harmless lookups. Assumptions about time, currency, and identifiers should be documented because these assumptions control how measures are interpreted and compared. Time can mean event time, processing time, or reporting time, and confusion among these can change trend lines and cutoffs. Currency can require conversion rules, consistent rounding, and clarity about whether values are nominal or adjusted, because mixing them makes comparisons misleading. Identifiers can change meaning across systems, such as customer ID formats or product codes, and mapping rules determine whether records match correctly. On the exam, stems sometimes include subtle hints like time zones, fiscal calendars, or multiple source systems, and these hints point to the need for explicit assumptions. In professional terms, documentation is not paperwork. It is the record of what the data set means, which is what allows others to trust and reproduce results. Validation should include checking totals before and after joining tables, because this is one of the simplest ways to detect duplication, missing matches, and unintended filtering. Before a join, a fact table has a known number of rows and a known total for a key measure, such as total revenue or total count of events. After a join, the row count and totals should behave as expected, and if they do not, the difference is a clue about the relationship between tables. A sudden increase often signals one-to-many matches where one-to-one was assumed, while a sudden decrease can signal unmatched keys or accidental filtering. This kind of validation is also useful when dimensions are updated over time, because changes in dimension keys can affect how facts attach to labels. Exam questions that mention mismatched totals often reward the candidate who thinks in terms of these before and after checks rather than jumping to conclusions about the analysis itself. A helpful memory anchor is to hold a simple phrase that ties meaning to function without getting lost in jargon. Fact equals measure, because facts contain the numbers that are aggregated and compared. Dimension equals label, because dimensions provide the descriptive context that makes those numbers meaningful to humans. Slowly changing dimension equals label that can change over time, because descriptive context is not frozen, and reporting must decide whether history matters. This anchor is not a substitute for modeling skill, but it keeps the core concept accessible when a question stem is long and time pressure is real. When a candidate can return to that anchor, it becomes easier to reason about joins, keys, grain, and history as parts of one coherent model. That coherence is what the exam is trying to validate. To conclude, schemas create trust because they define what tables mean, how they relate, and how reporting stays consistent across time and across users. Facts are measurable events, and dimensions are descriptive context, and a star layout makes this relationship easy to query and explain in reporting scenarios. Keys keep relationships stable. Snowflaking trades simplicity for reuse and complexity, and slowly changing dimensions force explicit decisions about whether history is preserved or overwritten. Grain clarity and join validation protect against double counting, and documentation of time, currency, and identifier assumptions protects interpretability and auditability. One practical next step is to describe aloud a simple schema sketch for a familiar scenario, naming one fact table, two dimensions, the grain of the fact, and how a changing attribute would be handled over time. That spoken sketch turns dimensional modeling into a usable exam skill rather than a set of disconnected definitions. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.